scientist, senior scientist. He will be giving a talk on microscopes for automated data collection. I have asked him to give a small intro about himself. So, Rishi.
Thank you. I'd like to thank the organizers for inviting me here in India to speak on behalf of FEI, especially to Natesh. So yeah, we're very happy to give a talk and to explain how we use our microscopes for automated data collection. So I did my PhD in the lab of Marin van Heel in London, and then I did a postdoc in Professor Steve Fuller's group in Oxford. Then I went to the MRC in London before going to Leiden University to run the Neeson Centre, which has 2 Titan cryosers. And following that, I joined FEI as a senior applications engineer. So I have quite a bit of experience with the Titan cryosers, and I'm just going to go through how we use the Titan cryos and also the advantage of automated data collection. Okay, so when I was doing my PhD in London, I had 2 good teachers. One was Elena, who's here today, to teach me the image processing, and the other guy was Brent Gowan, who taught me a lot about microscopy. And yeah, we had to make our own holy carbon grids, which was quite challenging to make. And once we made those holy carbon grids, which were on our copper grid, we then put our sample on there. My particular samples was ribosomes, and then we used one of these devices, kind of a freeze plunger. I'm sure you've all seen these kinds of devices. This is quite a manual device, so we would load the grid onto a pair of tweezers, put it on here and freeze it in this ethane slush, which is kept cool by liquid nitrogen. That would be in some device like this. We had some advancements, making a humidified chamber and some mechanism of automatic blotting, but this was still a very manual procedure. We would then take that grid and put it in one of these type of microscopes, which had limited software, so we couldn't manipulate the electron beam as flexibly as we can these days. But we would put our grid in here, and then we would have to search our grid, which was quite time consuming, set up our search parameters together with our exposure parameters, so we know we were taking a picture of the same thing we were seeing in low mag and then in high mag, set up our focusing procedures, and then shoot our image. So we were kind of shooting images quite blindly. We would then collect those images on the film. So a film cassette would only contain something like 56 of these films, so we would only have 56 images per cassette. So in a day, maximum we'd have is 112. And still we couldn't see what we actually took a picture of, because what we'd have to do once we collected all these films, here's the film that we used, was to go into a dark room like this lady has done, develop the film, fix it, wash it, leave it to dry, and then we would have our negatives. When we had our negatives, we would go to a scanner, so a kind of a really good scanner such as this one here, a Zeiss scanner, and scan the negatives in order to digitize them such that we could process it. And of course this process itself is also quite lengthy. So we'd have to take our negatives before we scanned them and look at them in an optical bench just to see if our negatives were any good. So not only if particles were on there, but if images were drifting, if There was low resolution in the images, so an image can look fine in terms of the amount of particles you have on there, but you could still have kind of low information. And we essentially wouldn't know all of this until we reached kind of this stage. We would then select our good negatives, scan them in, which took some time, and then we could do some processing. So all this takes some time. Okay, so here's the kind of manual bit. But nowadays, so 10, 15 years later, we have kind of more automated microscopes, plunging devices, and so forth. So our microscopes are now more automated in terms of the software we use. So we can now control quite precisely the electron beam. So we have a lot of flexibility in what we can do with it. For example, we can store hundreds of alignments if we need to, and load them up whenever we deem fit. And that's very important for automation. We also have automation in terms of freezing of our samples, so we can control the blotting time, the blotting force, the humidity, the temperature, and all these things make it much more consistent to get the same ice thickness across a particular grid. So this is our most recent one. Other companies such as Leica have a freezing apparatus, and so do Catan. And the other big thing which has helped with automation is these kind of digital devices in earlier cases, so the CCDs, and then these CMOS sensors, these kind of metal oxide semiconductor type technologies, which have really made a big advancement in what we can do, because now we don't have to take films, develop them, let them dry and then look at them. We have an image instantly which has a good signal, and which we can tell how good our sample is. Okay, so here's just kind of the workflow that we use for automation. So we have the biochemical preparation, which is really important. So if your biochemical preparation is not good, your sample's not homogeneous, for example, even if you put it in a Titan cryos, you are not going to get 3 angstroms resolution. You need to have your biochemical sample very good. We then take that sample and we put it on a grid. Now, the surface chemistry of that grid is also very important. So whether you're using carbon, whether you're using gold, how long you glow discharge, all has an effect on the protein that you're putting onto that surface. So that you have to look at carefully as well. Then you can establish your freezing, your blotting times, your blotting force, and your humidity and temperature, and all that in the Vitrobot. You then take that grid, you image it in one of our machines. So here we have a Talos, and we have various programs which we can use for then data collection in an automated way. Then, as you've been doing, you have your image processing procedures, you get your reconstruction, you do your structural analysis and all your annotations, and then you publish, hopefully, in a nice journal. And yeah, if you're quite fortunate, you can image in a Titan cryos, which is one of these here. So I'm just going to now just concentrate on kind of this section in terms of the automation, i.e. getting multiple grids into your microscope and setting up a automated data run. Okay, so this is how we mount things in our Titan cryos, or really any system that has our autoloader, like the Talos Arctica. So this is the grid. So this is where we would put our sample on. Then we have a mount where we load that grid onto, and we call this an auto grid. So it's this thing here. We then have a clip that then secures this grid in place. And then this whole construction is then mounted into the microscope. So this is how our grid looks like when it's ready to go in. So we then put it in our microscope, use our specialized softwares to look at the sample. We get an overview of the grid, so this is a portion of the grid. We can then zoom to any hole that we choose, for example this one. And then from here, take images of our sample. And I'll explain this in a bit more, this procedure in a bit more detail now. So all this is done under liquid nitrogen, but here it's done dry, so you can see what is going on. So here we have that grid that we showed earlier, and here is that little auto grid that we mount the grid into. We then use this white tool to have that little clip, and that is then fixed onto the grid such that we have our mounted grid. We then put that in for example, a container. And then this is now our mounted grid. So we transfer this to this device here, which is which we call a cassette. So this is a cassette, and it has 12 positions. So we can basically fill 12 positions in this cassette. So we can have 12 grids. And this also helps with automation. So we can look at 12 grids at a time once we've set this up. So we have 12 grids put in, and we can look at each grid. So we can't look at 12 grids simultaneously. We can look at one grid at a time, but we can all do that from software. We don't need to mount more grids. We just do it once, and that's it. We then have this tool to put that cassette with the loaded grids into this device here, which is called the nanocab. And this kind of cup will then go onto our system here. So you have your grids in the cartridge, and now get positioned in this cab, and the cab now gets positioned into the microscope. Right. So this is the heart of a Titan Cryos. So we have our cassette, which initially gets put in here, this cab, and this system is the autoloader. So it's both on the Titan Cryos and the Talos Arctica. The cassette then gets picked up by the autoloader, so it gets positioned in this this portion of the contraption. And then we have another arm, which is here, and it grabs a grid, retracts, another arm pulls up, and then the grid, which is retracted, gets put into the column of the machine here. So this is kept cold with liquid nitrogen, this autoloader here. And this is the Titan column. It has some automatic aperture system here. And this particular Cryos, which is in Neeson in Leiden, which have two of the Cryos machines. This one has a CS corrector, which is down here, which is what the CS is. So yeah, the Titan Cryos is a nice machine to have, but we also have other machines which are good. So this is the Titan's kind of little brother. It's called the Talos Arctica, and essentially we're adapting the Cryos technology onto the Talos platform. So this has an objective lens which has a constant power lens. So it's a C twin. On the Cryos, all the lenses are constant power lenses, which makes the machine, of course, much more expensive. But the Talos still has an automated kind of approach, so we can have unattended high data throughput due to this automation, which reduces the time it takes to get a good result. So again, we have this auto loader where we can load up to 12 samples. We have auto filling of liquid nitrogen, so we don't have to fill manually the machine or the holders with liquid nitrogen. This is all done automatically. You just pull a tank which is full of liquid nitrogen, and it can go for a week. And then you can use our tailor-made applications such as EPU and TOMO4 on this device. And you can get excellent quality data from a Talos Arctica. It's optimized from 80 to 200 kV. For 300 kV, you need a Cryos. Like I mentioned, it has a constant power twin objective lens. It's relatively contamination-free sample loading. And you have an increased sample lifetime. So over time, your sample will contaminate with ice, but it's very reduced in these systems. And what's good also, it's upgradable with all our upcoming developments, like the phase plate or the Falcon 3. These are all upgradable modules to this system. Should you not wish to have, for example, like an autoloader, and you wish to have a normal holder, you can use this machine, which is the Talos. With these systems, you do have to manually fill with liquid nitrogen, so it's not as automated, but still, it still kind of keeps hold of some of the automation that we've developed. So, for example, you can use EPU on here and TOMO4. You can have a SATA camera, which is quite a good camera as well. So it's kind of a CMOS with a scintillator, but it's still very fast and good camera. And you can operate it remotely, so you don't need to be in the same room. So with the microscopes of a few years ago, you would need to actually be in a room which would usually be dark for kind of several days taking pictures. Now you don't need to. The machine, you can set up the machine remotely from your office once you've put your sample in, and then you can operate things from your office. You don't need to be at the microscope. So what are our dedicated software applications? Okay, so we have EPU, and this is our kind of automated single particle data acquisition program. It means out of many, one. And then we have TOMO4, which is used for our automated tomography data acquisition, which is also very automated. So this is just the principle of EPU. We have our EM grid, which we would like to image. We would then like to kind of specify squares in that. And then from those squares, one thing I should also mention is that we don't need to make our own holy carbon grids anymore. We have companies like Quantifoil, which have these regularly spaced holes in the film. So this has also greatly helped with automation, because we can just search for these holes and move along one by one, which I'll explain later. So we have these holes, and we can select one of those holes, and in the holes contains ice, vitrified ice, with our particles in. So we want to go from here to essentially imaging here. And that's the principle of EPU. But I should mention that really the initial work for this kind of mechanism has been done in the Scripps lab with this program Leginon, which is available. Okay, so this is essentially how our EPU program works. So we have a grid which is in the microscope, and at a low mag with a low electron dose, so low that we can't really detect it, we basically take images across the grid, and then we stitch them together. So we have what we call an atlas. So this covers the whole grid. We can then identify the squares in that grid. And even from this magnification, we can already kind of tell what kind of ice we would like to select, because we can see which ice is quite thick. We can also see any empty squares, which we don't. Both of those we don't want to select for. So we just try and select the squares which have good ice. We can already do that at that mag. So then we take these images, which are at a slightly higher mag, to identify these holes where our sample is in. So we firstly have to measure the diameter of the holes, and then the program will automatically find all these holes. So we don't need to ourselves go to each area and look. We can also select for the ice quality in these holes, so we're trying to get ice of the correct thickness. And once we have these holes, we can then try and work out some acquisition schedule. So here in the yellow is going to be our exposure acquisition. So we can position 6 exposure shots around a single hole, and we can control the optics so precisely that we really are at these positions. So on the old microscopes we could basically just shoot one shot precisely, but because of the stability of our current microscopes we can do this kind of mechanism of acquisition. So the square here is where the picture will be taken, and the round bit is the size of the beam. So we position a little bit on the carbon just so we get a nice stable image and reduce the amount of drift that we have from our images. Here we have like a focus spot where we can do our focusing on, but that is all done by the machine. The machine uses some beam tilting procedures to automatically get focus, and then we can set the focus to what we wish. And then the microscope will just go away and collect on all the holes that we've selected before based on the ice quality, and it will take 6 images in each of those holes, and that's how we collect. So we don't anymore need to go to each hole and manually expose each time. The machine will do that for us now. And here's just the overview of what's happening. So we have our atlas, which is the whole grid. we have a kind of a square here, which is what this represents. We can see all the holes where the sample will lie. Here's a high magnification so that we can actually see the holes, and then we take an image in there, and that's all done automatically. We don't need to be involved any further. And something like this can run for 3 days, and it's fine. And we'll collect something like 4,000 images from this. Okay, so I've been talking for the last 20 minutes about how good automation is. And some of these publications have used the automatic procedures, but some haven't. I mean, I've taken a few of the actual data sets which have gone to these reconstructions, and I've done them with our automatic software, but some of them haven't. So I'm not saying that you need to do automation in order to get to a high resolution. You can get to a high resolution without automation, but the point is it's a lot more difficult, and you can't go to a facility such as Neeson or Diamond and really hope to get a high resolution structure in the short amount of time that you're allocated using non-automated techniques. So the automation really helps in the efficiency of high throughput data collection. So now routinely using automated procedures, we get to below 4 angstroms, really below 4 angstroms for ribosomes. Here are some more high resolution reconstructions of membrane proteins. Again, some of these have been taken with automated procedures and some not. But you can get to similar resolutions of things. Okay, and then here's some more examples, some of which I've taken the data for as well. Right, and this is just the last slide, just so I can show the improvements which have kind of led to the improved resolution over the years. So I think one of the important things, like in the 90s, was the introduction of the field emission gun to give a very coherent beam. And now we have the XFEG, which is an even more coherent beam than the FEG, and even more, the source is even brighter. And that's made a big difference to the resolution jump that we can attain. The other thing was the software. So now our software is very versatile and robust. So we can really control the lenses and the deflectors of the machine very precisely, so we can manipulate the beam well without any latent thermal drifts. And the last thing, which has been very important, is the direct electron detectors, such as Falcon 2 and soon the Falcon 3, and also the K2 from Gatan. These have been really important in pushing the resolution limits that we are currently achieving, and also making us achieve those resolution limits with kind of relatively short collection hours. So that has been a huge improvement. And it's just left for me to thank you for your attention, and if you're interested, please visit the FEI website for more information and details on our products. Thank you.
Thank you, Rishi, for a nice talk, quick and good overview of the automated data collection pipelines. Any questions? Mohit?
Hi, thanks for the nice overview. I just have two questions actually.
Sure.
So one, like regarding the EPU, so
Mhm.
you have shown the images.
Mhm.
When the program is running, it collects the images, but the images looks very crispy at that time. I mean, it looks like the defocus value is really high, but when you see them on other computer or something, they look different. So, I mean, I didn't get that much time to play with the software, but is it something that you also encountered, or you? So, I mean, you have like you go holes, then you have this whole image, how the
Yeah.
program is collecting.
Yeah.
That image, I mean, I have looked at your one slide.
Mhm.
They also looked very crispy. Can you go back and? Yeah,
This
this
one?
one. Yeah. 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 So down one, it looks like that is a very high defocus.
Mhm.
But when you look them in the on a different computer, you collect from the EPU and you looked in the different computer, they look different. So there is something different here. I have no like
Yeah.
technical details of.
No. Well, it depends, of course, the defocus that you set, what your contrast level will be, and generally you would have to set it based on your CTF function and what you would want to cover in your spatial frequency range. But generally, the image here will look sharper, essentially because it's smaller, so you get a coarsening just from that. And when you look at it on the screen, if you look at the real raw image, it's quite a large image, so you won't see that. You won't get that coursing phenomenon occurring. But generally, if you take images at somewhere between -2 microns defocus to like -4 microns defocus, that's a good parameter. If you're using something like the Falcon 2 or the Falcon 3 or the K2, that would.
So I used to take like at -3 defocus value, but I mean in comparison to this image what I'm getting from the CCD on the screen, they look really different. I mean just now about zooming it or something like that, but even like you have the like whole image, it looks more crispy, and that confuses me because I put like -3, it looks like it's -6 or 7, and that is something which bothered me when I do the data collection.
I think that's I mean, there shouldn't be any difference.
Okay.
There is no difference.
Okay, there's one more question. So you said about contaminant-free loading of the samples, but I think the contaminants are mainly coming when you freeze the sample, isn't it? Like when you have the liquid nitrogen or some contamination in the ethane. Most of the contamination comes from there, right?
You can get contamination kind of at all aspects. So you can get it when you're freezing. You can get it from dirty nitrogen. So you have to make sure you filter your nitrogen, make sure it's clean. And then you've got to work in an environment which has low humidity.
Yeah. What I'm asking is like contaminant-free loading. How you like compare it right now and in the Titan? Like if I have a Polara.
Right. If you have a Polara. Yeah.
In that you have a long,
you have to pump a long time. You have to pump a long time in the Polara because you have to put the arm on there, pump that, use the station to do your pumping. With the Titan Cryos, it's a lot more easy. So you just load it in that device that I showed. You put in the cassette.
So you will be more quick then, I guess, right?
Yeah, because your mass, your volume is much.
So as soon as you put into the microscope, you reduce the time, and that's how you like minimize the contamination, right?
Yeah.
Okay. How you look to the Indian market commercially? I mean, you know that the funding agencies here are very strong, and I mean, it's not easier to get that much money to get a Titan Cryos. So how you look at commercially here?
Well, we're hoping that there will be some investment, maybe between organizations, such that you may have a facility type Titan Cryos where the members of the Indian community can come and use. But in the meantime, maybe sourcing some other places like Neeson, maybe Diamond, which may be useful once you have a good sample that you're very confident of, may be worth doing, yes. But we're hoping that the
you can do some promotion. You can give like a better price to us, and probably we can promote it. Right?
Well, yeah, that's something which the governors can.
Okay.
Can arrange.
Thanks a lot.
Yeah.
Thanks, Rishi.
Sorry.
It's a very political question.
Yeah.
Thanks, Rishi. It was a very nice summary of your instruments. I have a couple of specific questions regarding your Talos Arctica and Titan. So, do you have any data which is done, for which a particle 3D reconstruction was done for the same sample in Talos Arctica versus Titan with the same detector configuration? Is something you can comment on? What's the quality difference between the two?
Well, the Talos is a 200 kV machine, whereas, for example, the Titan is a 300 kV machine, and the detectors are optimized for 300 kV. So you will get better DQEs at 300 kV. So your data is going to be better on a Titan, and additionally, the stability of your beam is much better it's better on a Titan Cryos because all the lenses are constant power lenses. So that means that essentially we have like 2 coils that go through each lens. It's not just one coil. So if you have one coil, you have a current, you change that current, you have a kind of a latent thermal properties. So you get hysteresis, it's called. But with constant power lenses, because we have 2 coils and current in one goes one way, current in the other coil goes the other way, we can essentially maintain the same temperature in that lens. And that means that the beam is much more stable. So the Cryos has many kind of improvements on the Talos Arctica. But the price is very different as well.
Of course, yeah, but somewhat related to that, has there been any published work with single particle work from a Talos Arctica so far? And what kind of resolutions?
I would say you can get to a pretty decent resolution of 4 angstroms, I would say.
In best of cases?
In the best case.
Okay.
Yes.
Something unrelated, particularly with regards to your EPU software. You were showing that those 6 regions that you pick on the hole actually include the rim of the holy carbon.
Yeah.
Why isn't it that you're taking a region within the hole itself, which is supposed to have the thinnest ice?
You can, depending on your sample. Some samples, for example, in the middle won't go because of the size, so they'll be positioned on the outside of the hole, and in that case you'd have the 6. For samples that are kind of evenly spread in the holes, then you may want to take the center bit, but you still have to expand that beam such that it hits the edge of the carbon.
Okay. So you have flexibility to do.
You have flexibility to do what
Thank
you choose. Yeah. Sure.
Does EPU handle this autofocusing in case of carbon and gold grids equally well?
Yeah. Gold grids are fine as well. They, in fact, have a very good signal, so they can focus perfectly well. Okay. The only thing with gold grids is when you do coma free, then you need some amorphous signal like carbon to do that. But focusing is not a problem.
Okay. Thank you.
Hello. Yeah.
Hi.
Thanks for the nice talk. I have a very general question actually. You said some of the advantages and applications of automated microscopes. Example, Titan cryos. May I know the limitations of it or any disadvantages in terms of data collection from data processing?
Any disadvantages?
Yeah, specifically Titan cryos.
It's a pretty good instrument. I can't really, I mean, there's some kind of issues if, yeah. The challenge would, I suppose, be expensive. It is, yeah, well, yeah. But they are expensive instruments to make. With the early autoloaders, it used to be. But now with the Mark III autoloaders, they're very reliable. Sorry? Mark I was a problem. Yes, I had a Mark I at Nissan, so we had to do a maintenance every 6 months, and then it was fine. But with the Mark IIIs, they're very, very stable.
I'm sorry, I have just one short question about that. Since you showed the picture, we have a CS character together with the cryo sometimes.
Yes.
So how do you comment the CS character in image? It's not the prop character, it's CS character, right? For the imaging. So how do you, so far as I know, the stability of the correction sometimes take only a few hours. So how do you comment the combination of CS character with cryos for taking a image for the biosamples?
I mean, there's no problem. Essentially, we set up a tableau with a certain detail.
Yeah.
And then it takes this tableau, and then once the tableau is taken, the software itself suggests or gives correction parameters.
Yeah. But I mean, do we get a lot of advantage and benefit from CS character?
Yeah.
Well?
Okay. So what was your question? What's the benefit for?
Yeah. Since it helps us a lot. Does it help us a lot for taking a cryo image if I use CS character? Or people just import CS character in cryos just in case they need a material science sample to study on this instrument?
I mean, for example, the machine at Nissan was used specifically to get higher resolution data. So it was the single particle machine. Yeah. And the machine without the CS character was the tomography machine. It's yet to be proved precisely how effective a CS corrector is with biological samples, but for sure you can better align the microscope with a CS corrector, and that offers definite comfort and assurances when you're trying to get the best optics you can. So, personally, I find the CS corrector very useful because I know exactly what my optics are, what limitations are, and they give me certain values. So I'm very confident in how good the microscope is performing. And then also what we noticed was that the contrast was more for a given defocus than on a machine without a CS corrector.
Yes, that's for sure.
So.
Thank you for the answer. Yeah, thank you.
So I have a question. So, if we need to acquire the images at different defocus values, is there any way to program it in EPU?
Yes, it's very simple. You just there's a little tab which you have, and then you just add in your defocus values.
Like the range.
Yeah.
Okay.
Yeah. You just put in.
Another question is that what would be the best configuration to install that software?
What will be the
best configuration of the computer to install that software actually?
The computer that comes with the microscope, that's the computer you will install EPU on.
So if that is the problem actually, we have a Polara, and the machine actually it was provided with the TIA software, and sometimes it gets hanged actually when we are acquiring images. So that's why I'm asking what should be the best configuration for this software.
Yeah, with the Polara. Yeah, it's which PC do you have?
Yes?
What is the machine? What is the PC that you have with the
It was
Polara?
provided with the machine only, FEI computer. I don't know what is the...
Okay,
the
I mean, because that should be more than sufficient to run EPU.
like the processor
Okay,
or RAM, if you say that.
Sayan,
not the graphics card.
maybe you can discuss this over the lunch.
Okay.
Yeah. I'd like to thank Rishi. We are running out of time.
Sure.
So I'd like to thank Rishi for a very nice presentation. I want you to collect this.
Oh, okay. Come
in the middle for this.
All right, okay.
There's a small memento for
Thank
the
you.
course. There's a Arunmula mirror from Kerala.
Okay, great. Thank you very much.
Metal mirror.
Thank you.